This is the hour before the dawn. In a few minutes, the stars will fade as the sun rises over the horizon. The same familiar sun that lit and warmed countless human generations before man recognized it for what it is. A nuclear furnace spouting monstrous hydrogen explosions 20,000 miles high. This is the power of the atom. The foundation of Britain's industrial revolution was coal. And for over 100 years, the demand for it rose relentlessly as more and more power was needed for an expanding industry. Above all, coal was consumed by the power stations, faster and faster. A new source of power was urgently needed, and to meet the challenge, British science and technology turned to the fundamental power of the universe itself, atomic energy. And the new giant went to work in silence. Calder Hall in Cumberland, opened by Her Majesty Queen Elizabeth in October 1956, was the first full-scale atomic power station in the world. And not only are the bright, clean buildings a startling contrast to their grimy, coal-fired relatives, but an effort of imagination is required to think of these neatly packaged cartridges of uranium as fuel for an industrial furnace. Yet fuel they are, and the operator of this charging machine is the lineal descendant of the sweating stoker of yesterday. From now on, world industry will depend more and more on nuclear energy, and behind the immense effort and research involved is Britain's Atomic Energy Authority's research establishment at Harwell. To Harwell come students from all parts of the Commonwealth and the British Isles, and from other lands as well, to learn something of the basic research and early development that will be needed to run the power plants of the atomic age. In this lecture hall, the fundamentals of atomic energy are explained, often by reference to British Experimental Pile Naught, affectionately known as BEPO, the forerunner of every uranium graphite pile now working in Britain. In this simplified diagram, we see that the bulk of the reactor is made up of the massive concrete shield which protects workers from the radiation produced at the core. The core is a block of very pure graphite pierced with holes in which uranium rods are placed, here enlarged. When enough rods are placed thus close together, a spontaneous nuclear fire begins. The chain of atom splitting, or burning, created by the neutrons will in time consume all the uranium-235 contained in the uranium fuel, and will convert some of the remainder to the concentrated nuclear fuel, plutonium. This chain reaction heats the uranium rods. Control rods, by absorbing the neutrons, can damp down the nuclear fire. To stop the reactor completely, both the control rods and special shutdown rods are used. The key to the use of the atom for power production is the heat generated by the burning of nuclear fuel in a reactor. At Calder Hall, for example, high-pressure gas removes the heat from the reactor. Steam boilers are heated by this gas, just as coal produces steam in a furnace. This steam is used to drive conventional turbines, which in turn produce electricity for the national grid. The operators of BEPO are therefore really working an atomic furnace, which is also a creator of radioactive products or isotopes. These consist of many different substances which are themselves made radioactive by the simple method of exposing them to the radioactivity inside Beppo. Radioactivity does not affect the ordinary properties of the materials, but adds a new characteristic which has hundreds of applications in industry, science, and medicine. Britain exports a greater volume of isotopes than any other country in the world. Many of her atomic products go out to the Commonwealth, from which comes much of the raw material of atomic power, uranium ore. Ever since 1948, heavy lorries have been rolling along this quiet North Country road to the gates of an ordinary-looking factory at Springfields in Lancashire. And ever since 1948, that factory has been processing an ever-growing volume of uranium ore to feed our soaring demand for nuclear fuel. Most of the chemical processes at Springfields are not peculiar to uranium, except that the greatest care has to be taken to protect workers against poisonous particles from the ore. These men are completely protected by the specially designed respirators which they're wearing. From the filters and the solutions, the ore arrives at the final stage, the chemical furnace, that behind concrete walls and fireproof doors will create at last the pure metal. This small igniter is sufficient to start off a fierce blaze within the furnace, reaching a temperature of 1500 degrees centigrade. The molten mass dulls and cools. Time passes, and as the doors roll up again and the heavy mold is opened, we see what it is that has been born in the fire of the crucible, the raw material of the second industrial revolution, uranium. The fact that uranium is a metal and can be worked is put to use in shaping the finished rods, which after being encased in light alloy envelopes are destined for the magazines of the great plutonium factory at Windscale on the Cumberland coast. Note the word magazine, for this is no coal hole or greasy tank, but the storehouse, clean to sterility, of the ammunition for enormous power. This is the Windscale reactor, hung about with ladders like Gulliver in Lilliput, and as high as a 15-story building. Windscale is unique. It is science fiction intruding on our sober lives. And it is a very great producer of plutonium, the pure atomic fuel for both industrial and weapons projects. To cool the huge reactor, batteries of fans drive air through a ventilating system around it, sucking in fresh air through banks of filters. At Windscale, the whole system of circulating air is rendered safe by a single master switch, which cannot be operated until all airtight doors into the system are locked. As the reactor is for plutonium production only, the great heat generated here, as in all reactors, is forced by the fans up through the flues and out of the massive chimneys towering far above. The experience gained in building the Windscale reactor enabled British scientists and engineers to take a great step forward in building the plant at Calder Hall. The heat from the reactor, instead of being wasted, is used to produce electricity by the simple expedient of heating water to make steam, which in its turn drives perfectly ordinary conventional turbines. The generating equipment at Calder could be in any big power station. Only the source of the heat for the boilers is different. In addition to producing heat, the Calder reactor, like those at Windscale, make plutonium, and both share a common plutonium processing plant. Under this still water lie the used uranium bars from the reactors, waiting for the fiercest radioactivity to subside so that they can be stripped of their light alloy casing, still under 12 protective feet of water, by the groping claws of remote handling equipment. In the reactor, part of the uranium bars has become plutonium, and now they are hoisted high up to the top of the separation plant in which the plutonium is extracted by chemical means. Here also, the radiation is too great to allow handling except under water, and some of the process is so screened by concrete walls the operator by the aid of a loudspeaker. Like every other part of the Atomic Energy Authority's work, this chemical process for separating plutonium is under constant review at Harwell, and already the research men are experimenting with a revolutionary smelting process as a possible alternative to chemical methods. The harnessing of the prodigious powers of nuclear energy means a research effort of unparalleled scope and complexity, and this effort is centered at Harwell. Harwell never rests on its laurels, and no new success in the application of theory to practice is regarded as final. Not even the grim association of plutonium with atomic weapons survived for long the ingenuity of the researchers. For plutonium is a pure atomic fuel, and behind this concrete shield is Zephyr, Europe's first plutonium reactor. Zephyr has shown that the strange phenomenon of breeding is possible. The plutonium in the reactor is surrounded by uranium, which itself becomes plutonium faster than the original plutonium burns away. Zephyr is an experiment. It produces no power, but it points the way ahead to the ability to generate power and yet to yield a dividend of more atomic fuel than is consumed. Another pure atomic fuel is uranium-235, which is produced in this giant factory at Capenhurst. The enormous building is needed to separate U-235 from natural uranium, and yet acres of elaborate factory are controlled by a few men using advanced automation techniques. New technologies are constantly called for to harness the pure atomic fuels. And this model of Harwell's experimental U-235 reactor, Dido, foreshadows the actual full-size reactor here seen under construction. The fast breeder reactor program begun by the Zephyr experiment is taking rapid shape. Here, constant watch is kept on the next step on the road to a fast breeder power reactor, the U-235-fueled Zeus. Beginning at Harwell as recently as 1946, the pattern of British atomic development has spread outward from its birthplace ever wider and faster. In universities, in hospitals, in industry, and in research, specialists everywhere are working on problems of atomic science. Far to the north, where the bleak Caithness coast faces the Orkneys, the great reactor at Dounreay, first child of Zeus, is raising its strange shape from the rocks. The huge globe at Dounreay is a symbol of Britain's atomic progress. But it and the breeder power reactors of the future, to produce electricity for the benefit of mankind, are founded on the manifold skills that British engineers have won over 200 years. Power from Calder is already feeding into the national grid, whilst continually improving Calder-type reactors are the foundation of the British nuclear power program of the immediate future. The more distant view unfolds as British scientists toil at the never-ending task of setting the hand of man over the power of the nucleus, the fuel of the universe that keeps the sun and all the stars alight. The foundation of Britain's industrial revolution was coal. And for over 100 years, the demand for it rose relentlessly as more and more power was needed for an expanding industry. Above all, coal was consumed by the power stations, faster and faster. A new source of power was urgently needed, and to meet the challenge, British science and technology turned to the fundamental power of the universe itself, atomic energy. And the new giant went to work in silence. Calder Hall in Cumberland, the same familiar sun that lit and warmed countless human generations before man recognized it for what it is. A nuclear furnace spouting monstrous hydrogen explosions 20,000 miles high. This is the power of the atom. This is the hour before the dawn. In a few minutes, the stars will fade as the sun rises over the horizon.